Hey, hello everyone. We are Bubble Stix. We're here to present our senior design project on hydrogen production. Our group consists of Christina Nordrum, Norelli Narciso, and myself, Olivia Ruiz. Our advisor is Dr. Eric Detzi. So the project wanted to focus on environmental issues, especially in the realm of sustainable transportation, which has become a worldwide focus. Countries like China, France, and Germany have all made it clear that they are trying to become less environmentally polluting countries, as shown especially by China is trying to lower their smog index as it has become a public health hazard in the past. And then all of these countries also have different kinds of sustainable transportation goals that we were hoping to capitalize on. So the current transportation landscape that we were looking at, we created a set of goals that we wanted our system to be able to achieve. So we wanted no pollution, safe fuel storage, we wanted it to be non-toxic, we wanted it to be easy to refuel, and we wanted our system to be easily recyclable. So the current market is mostly for gasoline combustion engine cars. These cars run off of gasoline, which creates a lot of carbon monoxide when it burns. Gasoline is not non-toxic, and it also cannot be recycled. The next option on the market that's really big is electric cars. And while they do have some better stats, the electrolytes inside the batteries in these cars is very toxic to the environment. It is not easy to refuel a car that is electric, as it takes hours to recharge, and you can't really recycle a battery very easily. One car that we were particularly interested in was stored hydrogen cars, and these cars do have a fair amount of pollution because they have to be run off of methane-created hydrogen, and it's not very safe to carry around a bunch of compressed gas or hydrogen for any matter because it's very flammable. It's not easy to refuel, as there's not a ton of hydrogen refueling stations across the country, and you can't recycle. Our system would create on-demand hydrogen, and it would do this through creating no pollution. It would be safe to store because it would be on demand, so no stored gases. It would be non-toxic because of what we're using. It would be easy to refuel, and it would be recyclable. To put this in perspective of the current hydrogen production methods is that methane is used and it's reformed into hydrogen, which has to be stored, and then this hydrogen is fed into a fuel cell to power a car. Our system would eliminate methane entirely and use nanoporous aluminum reacted with water, two very safe materials, to create hydrogen on demand. So this would eliminate both the use of methane and the use of a compressed gas container or compressed gas of any type. So our hydrogen is generated through aluminum and water, as I mentioned before. The aluminum is alloyed, and then this is processed into nanoporous aluminum, which is the powder you can see right here. And this nanoporous aluminum is hydrated, and it creates hydrogen. So a better schematic of this is shown here. As you can see, the nanoporous aluminum reacts with water to create hydrogen bubbles, and these hydrogen bubbles are fed straight into a fuel cell. The nanoporous aluminum becomes aluminum hydroxide, which is a commonly recycled material. The one thing we did have to watch out for was to make sure we had good seals on our system, because the aluminum can also react with the air to create aluminum oxides, and these reactions can be very exothermic. To talk more about our actual system, I'll hand it off to Norelli.
So as Olivia mentioned, there are different parameters that need to be considered. So because of that, we face different challenges. So we first started with our Stix idea. It was essentially a small cylinder which would have both the hydrogen source and the fuel cell inside. However, it was a really small system, so we couldn't put a cooling system inside, and the capacity was very limited. So we moved on to our next one. Our next design was a flat system. It consisted of two different parts. The top part would be the hydrogen source, and the bottom part the fuel cell. However, we also faced challenges with this one. Because it was larger, we couldn't maintain the pressure, so the pressure was too low to go for the hydrogen to go through the fuel cell. And also, we couldn't control the water release properly. So we moved to our next one. This one we called the salt and paper shaker. This one consisted of simply a cylinder which had the aluminum on the bottom and the water on the top, and we would have a mechanical lever that we would just press in your bicycle or in your scooter that would release the water into the aluminum, creating the hydrogen. However, the problems with this one was that we couldn't maintain the pressure of the hydrogen once it had started, and also the aluminum had to be completely sealed, which was a challenge. So we moved on to our next and final design, and we're here to present to you the bubble Stix, which solves all our problems. It has two parts. It is a two-part system. The bottom part consists of a water injection system, and the upper part contains a series of straws that are filled with nanoporous aluminum. This way, the thin straws maintain the pressure, and the system can be completely sealed. So now I'm going to explain to you a little bit how it actually works. As you can see here, we have a two-part system. The bottom part is the water injection system. It has a series of lure locks in which you can attach needles, and the needles go straight into the straws, and the straws are filled with nanoporous aluminum. And at the top, we simply have a collection box in which we collect the hydrogen. So if you look inside one straw, what you can see is that we have a needle that is completely sealed around with a sealing agent that we conducted tests on, that Christina is going to talk to you a little bit about later. It also has a rubber stopper that the needle goes in through, and then it reaches the nanoporous aluminum. So the water can go in through the needle, into the nanoporous aluminum, react with the aluminum, create the hydrogen, which is collected at the top. The system uses gravity to separate both the hydrogen, the aluminum, and the water, and also capillarity, so that way the water can go both up and down. And we still use a mechanical system to deliver the water into the system, so that way we can insert very specific amounts of water using the water as a limited reagent and producing the hydrogen on demand. And the system is still completely sealed. So our next step was, let's prototype this. So we created we 3D printed a prototype, which is being passed around. On the left, you can see we have the straws, which are filled with nanoporous aluminum. And on the right, we have the water injection system, which has all the needles. We conducted some tests on it. Unfortunately, it kind of warped a little bit, so we had to come up with an additional testing system that now Christina is going to explain a little bit about.
Great, thank you. So we started with a bit simpler of a testing setup that was a syringe filled with water and connected to a pump so we could control the water insertion rate, as mentioned, which was then connected to just a normal plastic straw that was filled with our nanopores or aluminum, and that, as the water fed into it, would react and form hydrogen, which we could collect and then feed over to a fuel cell. Fuel cell generates electricity and is used to power various devices. So what were our objectives when we were testing this? First, we wanted to make sure that we had that water and oxygen tight seal. That was really important. And second, we wanted to make sure that we were producing sufficient hydrogen for the fuel cell so that we could get a constant current and a constant power output. So you don't want whatever device you're using to stop working halfway through what you're doing. So first, the water and oxygen seal. As Norelli mentioned, there was a very specific sealing area on our design. And because our system is obviously in contact with water all of the time, many adhesives have trouble in water and can break down, so we decided to test them by just submerging the seals in water. We found that a Loctite was the best option. It's actually, there's still needles attached inside the straw part of the sample that's being passed around. And then 2 types of hot glue, which didn't do quite so well in the water. For our final design, we chose to use a Loctite plus the hot glue that's clear, so that we would have a doubly safe mechanism for sealing and just make sure there were absolutely no chances for air to escape. So then we wanted to know, did we produce hydrogen? And the answer is yes. When you fully submerge the nanoporous aluminum, you get a beautiful curve of hydrogen production. Because we are using water as our limiting reagent, we're only focused on these first 2 points that show significant hydrogen production in a very quick amount of time. And then we tested if we just attach a simple balloon. This is actually a finger of a lab glove, and we were able to inflate it, as you can see in these 2 photos. So then we tested, as mentioned, the current. Can we get a constant current output? And after a few different types of water injection, we were able to maintain a 10 minutes of constant current, so that's power for 10 minutes for any device. And then we moved to a higher current, higher power for about 2 minutes before completing the test. And again, this was all done with just 1 straw. So we then said, well, what can we power with our 1 straw? So we started with a fan. So in this video, you'll see a fan running, and then it'll move to our prototyping setup. The straw and the syringe. So that was great. And then we went, well, we want to talk about transportation. So let's try testing a very small car. And so this was fully run on our hydrogen.
The car. Norelli's in there.
This is what you'll be driving in tomorrow. So as I mentioned, we want this in the real world, right? Like we want your cars running on sustainable hydrogen. So with one straw, we were able to power a fan in a car. With 64, we found that we could successfully power an electric scooter, which are becoming more and more popular in cities such as San Francisco, New York, even as far as international cities. So we compared what happens when you look at our straws versus the current batteries in scooters. Current scooters can go a distance of 10 to 20 miles. Their weight is between 10 and 30 pounds, and they have a recharge time of 2 to 10 hours. All pretty impressive considering the new technology. However, ours were able to go the same 15 miles. They were actually lighter weight at just 7 pounds, and they have a recharge time of 10 minutes, and that's just considered to be the time it takes to remove one bubble Stix and put in another one. So they're also fully mobile charging stations because you carry it with you. So in conclusion, we were able to create a fully sealed high-pressure system to produce hydrogen on demand. We then tested this system and saw that we were able to produce a constant current and a constant power output from it for over 10 minutes. With just one straw, we were able to power a car and a fan, and we believe that we'll be able to fully integrate this into the future of transportation. And in fact, we're looking to get a patent on this design in the near future. So we would like to acknowledge this project, Dr. Eric Detzi for advising, the Berkman Fund for Undergraduate Innovation at Penn Engineering for their funding of the project, John, Dongyang, and Tim in our lab, Steve at LRSM, Dr. Vanessa Chan for her guidance on this project, and also Vicki Lee for her eternal love. Thank you. And we'll take any questions you have now. Yes.
I thought that what we're going to do is put the, what is it, aluminum?
The nanoporous aluminum, yeah.
And put it in a container, let it generate hydrogen, and store that hydrogen to produce a car. Why would you do it that way?
Compressed gas is super dangerous. I don't know if you heard the story at University of Hawaii. There was a broken gas casket that actually took off a girl's arm. So having that in a... They do. It's possible, but those have such a high weight needed, like those are steel containers, which is very heavy and dense, that they don't compare to current like gasoline, so no one will buy them because you can't create an effective, like a power capacity.
I mean, so how much of this material do you need and how much water to create?
So for this, the one that, for the scooter example that we showed, that was 300 grams of aluminum and 600 grams of water.
And it
So.
for how long?
And that runs, like I said, for about an hour, which is exactly on pace with other scooters.
So the powder is contained in the bubble stick?
Yes.
And then you have to add water or add water to it?
You'd have to add your own water, but
So you, like, any water will do, you get tap water?
probably distilled water, but they are deionized, sold at like local drugstores kind of thing.
But what if you were to attach it to like an array, the Toyota car, right? I mean, how much gas would you have to generate to fill a tank?
RPI is actually working on a project with that, so we haven't scaled it up that far, but I know they are working on it, and it's been, like companies like Toyota are also very focused on on-demand hydrogen, and I know Hyundai is also, these things are all very under wraps, because while there are the containers that can take a bullet, they're very expensive to produce, and it would just be much easier if we could use something like aluminum, which is recycled all the time.
So for these, we're able to get the cost of a bubble stick down to about $2 per cartridge, which is extremely cheap.
So on the scooter, you're producing hydrogen to then convert to electricity for the
Yes.
fuel cell.
Yes.
In a car, would you be doing the same thing, or would you be powering the motor?
It would be an
So
electric
it's
vehicle.
an electric car.
Yes.
Yes.
So what's the environmental impact on the aluminum itself? I mean, I know you said you're using recyclable
Mhm.
metal, but would there be sufficient supply of aluminum to basically unify electricity, right?
Yeah, so I mean, aluminum is one of the most.
Because of how it's mined right now, that's not super sustainable, but the thing is, once it's in the market, if it keeps getting recycled, especially if you have something like a car, where if you design gas stations to be able to take these, you're going to be recycling it over and over and over again. So,
And the best part is both the pre-product and the post-product can be recycled, so there's no separation process necessary for the used aluminum.
Well, to put energy somewhere to get the pure aluminum.
Yes, yes.
So that energy has to come from some type of fuel.
Well, any fuel source takes energy to create.
I'm just curious, how does the weight of this for the current generated compared to a battery? Because if it's lighter, it seems like aside from this kind of transportation thing, it might be something for backpack.
So that was the original, the first design we considered. The HydroStick design was a AA sized thing, and there were a few problems with just the overall like cooling and that sort of thing, because you don't want it in a super confined space, right? Like transportation is easy to cool, but it is totally possible to scale to that. Yeah.
Yeah, ideally that would be what would happen with this, and eventually on-demand hydrogen would be a really great resource, because these are our system. Right now it's just working down this. Our system is very light compared to like a general battery or something like a car engine, but it's working down the size of a fuel cell. So we were just working on feeding the fuel cells, but once they continue to reduce the size of the fuel cells we're feeding, it's really going to be something that could hit the market.
And just to be clear, the fuel cells are ready for like the car scale. It's just they don't have small enough ones for like a backpacker scale.
Thank you very much.
Thank you.